three-phase power cable temperature. We have a three-phase power cable laid in the open air. The alternating current flows in the conductors, and the conductors heats up. Our task is to calculate the cable temperature. This task consists of two parts. First, I need to simulate AC magnetic problem to calculate the current density distribution and to calculate the Joule heat losses. Then I'm going to pass the losses to thermal problem to calculate the temperature distribution. And then you will find out that the conductivity of the conductors depends on its temperature. So we need to return to AC magnetic problem, correct the conductivity value, run the analysis again, find the new value of the Joule heat losses, and run the thermal analysis again to find the new value of the temperature. So it's an iterative process, and we need to run the analysis several times till the temperature value converges. Okay, let's start QuickField and see how it could be done. In QuickField, I create new problem, cable AC. Next, problem type is AC magnetics, frequency is 60 Hz. I'm going to simulate only a cross section of the cable, so the model class is plane parallel. Length units are millimeters, and I'm going to calculate losses per 1 meter of the cable length. Finish. Here you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. Here I have the file, and I'm going to import the model. The model is imported, and here you can recognize conductors, insulation, screen, jacket. Let's assign labels. For labels, you can explain the geometric object's meaning and provide material properties. Switch to Select Objects mode, click to select the conductor, and type in the label name here. This is conductor A, B, C. This is zero conductor. This is the conductor's insulation. Hold Ctrl button to select multiple objects at the same time. This is filling. Again, several blocks. This is another layer of insulation. This is the screen, and this is the jacket. Now that's all for block labels, but in fact the magnetic field is distributed not only inside the cable but also in the air outside. So I'm going to add the air block. QuickField cannot simulate the field distribution in the infinitely large space, so I should limit the simulation domain. Switch to Insert mode and draw the air block boundary away from the cable. Far away from the cable, the magnetic field fades to zero. So at this boundary, I'm going to specify zero magnetic field boundary condition. I assign label boundary. And this block is air. Now let's provide physical properties for these blocks. Air, magnetic permeability is 1. For all insulation layer is the same, magnetic permeability is 1 and 0 electrical conductivity. Screen, let's zoom in. Screen is made of copper, which electrical conductivity depends in fact on temperature. Here you can see the file with the electrical conductivity dependency on temperature. And in QuickField, I click depends on temperature, and I need the table of two columns, temperature and the conductivity. Okay. I need this column, and I need this column. Okay, copy these values and paste it here. That's for the copper. Shield is counted at one side only, so the total count in the shield is 0. Total count 0. Okay. For the conductor phase A, which is made of aluminum, the permeability is 1 and electrical conductivity is a function of temperature. Let's copy this and paste it here. And the total current in the conductor A is 150 amperes. This is the root mean square value. In QuickField, I should specify the magnitude of the sinusoidal wave. So this is times square root of 2. SQRT. This is the magnitude, total current. Okay, for the conductor phase B, again, depends on temperature. The same total current of 150 amperes multiplied by the square root of 2. But this time the phase is shifted by 120 degrees. Okay, and for the conductor phase C, which is made of aluminum as well, the total current is 150 amperes, but the phase shift is 240 degrees. Okay, and in zero conductor, there is no electric current because we have the symmetrical three-phase system. Anyway, I specify the electrical conductivity, and I specify that the total current is 0. Now you see that we have specified electrical conductivity as the function of temperature, but what is the temperature of the cable? Let me guess. The air temperature is 20 degrees, so let's the cable temperature to be 40 degrees. So for these labels, I specify the temperature of 40 degrees. This temperature value is used to calculate the actual value of electrical conductivity. And for the screen, the temperature is 40. Okay, that's all for block labels. As I said, far away from the cable, the magnetic field fades to 0, so at the external boundary, I specify 0 magnetic potential. The geometry model and the data are ready. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Save all problem files and solve the problem. Problem is solved. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density distribution in the conductors. You see, we have specified 0 total current in the shield, but there are eddy currents in the shield, so there are losses in the shield. You can calculate the loss value using the contour tool. Click any block, follow to the integrals, and here is the draw heat power generated in this conductor per 1 meter of the cable length. And in this conductor, it is 6 watts. In zero conductor, it is almost 0, and in the shield, it is 0.4 watts per 1 meter on the cable length. My task is to calculate the temperature. Remember, I guessed that the temperature of the conductors is 40 degrees Celsius. Let's calculate the temperature distribution. In QuickField, I create a new problem. Cable heat. Next. Problem type is steady-state heat transfer. Model class is plane parallel. Length units are millimeters, and the model depth is 1 meter. And I'm going to use the same geometry model file that was used in electric problem. Cable_ac.moed. Click browse, and this is the file. Okay, finish. The geometry model already contains labels, but in thermal problems I should provide thermal properties for these labels. Thermal conductivity of aluminum is 247, and the same for all aluminum conductors. The screen is made of copper with thermal conductivity of 380. The insulation of the conductor has the thermal conductivity of 0.2, and this insulation, what is it? This insulation block has thermal conductivity of 0.2. The filling has the thermal conductivity of 0.05, and the jacket has thermal conductivity of 0.29. Air is moving around the cable. I cannot model this. Instead, I assign label to the cable surface and specify convection boundary condition. Cable surface. And for this label, I specified the convection boundary condition. The ambient air temperature is 20 degrees and the convection coefficient is 5. Okay. So for the air, I do not calculate the temperature distribution and I do not provide any physical properties. Just open the dialog and click OK. And here you can see the exclamation mark. This block is excluded from the analysis, from thermal analysis, but it is still a valid block label in magnetic analysis. Okay, for this label, I do not need to specify any properties, just click OK. I can copy the Joule heat loss value from magnetic problem and paste it here in thermal problem in block properties. But there is a better way. I can link two problems together so that the losses will be automatically transferred from the magnetic problem to the thermal problem. In order to be able to do so, both problems should be based on the same geometry model file. This is our case. Both problems use the same geometry model file. Okay, so in thermal problem, I open the properties dialog, follow to the link step. Here choose the link type, the generated heat, and browse for the problem that contains the data. This is our cable AC magnetic problem. Here it is. Open, add the link. Okay. Now you see in thermal problem there is a link and the generated heat is automatically transferred from the magnetic problem to the thermal problem. Okay, let's see this link in action. Let's solve thermal problem. The linked problem results are out of date. Okay, let's solve this magnetic problem once more. Solve. And we've got an error on resolved edge label cable surface. Indeed, both problems share the same geometry model file, and when we assign label to the cable surface, This label appeared both in thermal problem and in magnetic problem, so I should provide some physical properties for this label in magnetic problem as well. In fact, this label doesn't have physical meaning in magnetic problem, so I do not specify any properties here. Just click OK, and you see the 0 mark next to the label name. That means this label doesn't contain any physical properties, and this label doesn't affect the results. Okay, let's solve magnetic problem again and make sure we have the same results. Let's zoom in. Well, the current density distribution looks pretty much the same. Now let's solve thermal problem. Here's the results. Let's zoom in. And now you can see, I will use the local values tool, that the conductor temperature is 52 degrees, which is far away from my initial assumption that the temperature would be 40 degrees. For the zero conductor, it is 50.5, and for the shield, it is 48. Let's solve the magnetic problem again, but this time I will specify the actual values of the temperature. The temperature of the conductor phase A is 52. I copy this value, and in magnetic problem I now provide actual value of the temperature, so that QuickField will be able to calculate the actual value of the conductor conductivity. For the conductor B, the temperature is this value. If you have so few conductors, you can do it manually, but if you have a lot of conductors, you'd better use the automatic linking procedure. Okay. For the conductor C, it is this value. For the zero conductor, it is 50.5. And for the shield, it is 44.5. Now let's run the analysis again. I solved the magnetic problem, and I solved thermal problem. Now you see the conductivity has changed. We have the same current, but the conductivity has changed, so the losses value has changed, and we have got another value of the temperature. It was 52.4, now it is 53.8. Let's run one more iteration. Again, I will copy the temperature values and paste it here. Now the actual temperature is 53.8. And for this conductor, for the conductor B, it is 53.6. For the conductor C, it is again 53.6. For the zero conductor, it is 51.8. And for the screen, it is 49.8. So we have an average increment of 1 degree in this iteration. Okay, let's solve the magnetic problem again. And solve the thermal problem again. Now let's check the temperatures of conductors. 54 degrees, and on previous iteration it was 53.8. So we are pretty close to the final value of the temperature. You may continue iterations, or you can stop now. And here in thermal problem, you can measure the temperatures. You can use the contour tool to get the temperature distribution along the contour line and measure the temperature drop in the insulation. So this is conductor insulation layer, this is screen, and this is the jacket. And you see that the surface temperature is 48 degrees. And in magnetic part, I can use the contour tool and calculate the losses. Remember, the losses were about 6.1 in conductor phase A. Now it is 6.3. If you search for the three-phase cable temperature on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be viewed and the results may be opened using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.